Just like work and energy are related, virtual work can also be related to changes in potential energy. This gives us a slightly different way to analyze these statics problems, but still very similar to what we saw last class. Forces have the capability of doing work. When these forces are conservative, that work can be translated into a change in potential energy. A conservative force is one that does not depend on the path taken. All that matters is the overall displacement, 0.2 minus 0.1. Some examples of conservative forces are gravity and springs. The change in gravitational potential energy, which is the work associated with gravity, only depends on initial and final elevations, not how the object got there. It could move left, right, up, down, whatever. An example of a non-conservative force is friction. The longer the path, the more friction removes energy from the object. The work done against gravity is given by W delta y, where W is the weight of the object equal to the upward lifting force to get it to move, and delta y is a change in height of the object. ds is the actual displacement of the box, but again, only the vertical part matters, and so we get the cosine, which turns into just the vertical part dy. Again, this does not depend on the path, but only the change in elevation, so this is a conservative force. Also, in this bottom equation, this is the work done by gravity, as opposed to the work done by an external agent to lift the box against gravity. So there's a negative sign here, gravity going down, but delta y being the displacement in the positive or upward direction. Similarly, the force needed to compress or extend a spring is also a conservative force. The amount of work done during this spring displacement is given by 1/2 times the spring constant k times the overall displacement from equilibrium, x minus x0 squared. Notice the negative sign in this equation. It's a very subtle distinction. It really depends on whether the energy is coming in or out of the system. If this work is being done by this external force F to compress the string, then the work done on the spring is positive. The spring gains energy. But if this is the work done by the spring, then the spring loses energy, and so the work would be negative. This equation, with the minus sign, assume that the spring was our system. However, if whatever is causing the force is our system, then everything is reversed. No minus sign going into the spring. Whatever that system is would be the one losing energy. So be careful with that. This is similar to what we saw last slide for gravity. The amount of work done by a conservative force on a system is equal to the change in potential energy of that system. Since conservative forces only depend on position and not path, the potential energy of a system depends only on the position of that system. For this, we need to define an origin from which this position is measured. This is called the datum. It corresponds to where the object has 0 potential energy. Note that the value of the potential energy is not what is important, as we only care about changes in potential energy. Therefore, the datum can be picked to be any location, some being more convenient than others. For example, the ground is usually chosen as the datum for the potential energy, but really any point can be picked. Potential energy is generally denoted by capital V and is equal to the work delta U. Gravitational potential energy, V with the G subscript, is then defined mathematically as W times Y, where W is the weight of the object, and Y is the vertical distance from the center of gravity of the object to the datum at Y equals 0. If this is above the datum, the gravitational potential energy is positive. If it is below the datum, the energy is negative. Similarly, the spring potential energy is given by Vs equals 1/2 Ks squared, where S is the displacement of the spring from its equilibrium position, x minus x0, that we had on the previous slide. To use potential energy for equilibrium purposes, we want to set up the potential function, which is the total potential energy of the system. Here we have V equals Vg plus Ve. However, in general, it is just all the potential energies added together, whatever potential energies are involved. The other consideration is that it is most convenient to have this to be a function of a single variable, here represented by Q. This is generally an angle or location coordinate. Last class, we dealt with the work done to determine equilibrium conditions of certain bodies. Since work is equivalent to the change in potential energy, we are mostly interested in the change in potential energy. So work done delta U equal to U2 minus U1 is equal to the potential energy V at some location Q2 minus the energy V at the initial location Q1, or in derivative form, du equals V of Q plus dQ minus V at Q, or du equals dV. To be consistent with the previous day's material and virtual work, again here we're only considering virtual displacements from Q1 to Q2, therefore delta U equals delta V, and again the principle of virtual work means that this change in energy, delta V, should be 0, which means that the derivative of the potential function must be 0, or dV dQ equals 0. So an equivalent criteria for a frictionless system to be in equilibrium is that the derivative of the potential function be 0 at that point. This is where it is nice to have the potential function to be a function of a single coordinate q. If this were not the case, we would have to deal with partial derivatives. Another consideration is the stability of the equilibrium position. We haven't really talked about this when dealing with forces, but some equilibrium positions are stable, while others are unstable. The best example of this is a pendulum. If the pendulum is hanging straight down, it will not move, so it is in equilibrium. This is a stable equilibrium point because any displacement brings it back to its equilibrium position. If you push it to the left, gravity pulls it back to the right. Any equilibrium position where a displacement tends to send it back to the equilibrium is called stable. It is interesting to note that in this case, the potential energy function is a minimum. Remember that equilibrium corresponds to a zero derivative, which is also the minimum or maximum of the function. On the other hand, if you stand a pendulum straight up, that is also an equilibrium position. However, if this position is displaced, gravity will tend to push the object even further from equilibrium. This is an unstable equilibrium position. Again, here, it is interesting to note that the potential energy of this position is a maximum, again, meaning the derivative is 0. There's actually another option called neutral equilibrium. Another way to get a zero derivative of a function is for that function to be a constant. In this case, there is no maximum or minimum for that function, but still corresponds to equilibrium because the derivative is 0. What this means physically is that every position is actually an equilibrium position. If this object is displaced, it remains in equilibrium in its new position. A physical example of this is a double pendulum, one which is symmetric about the pivot point as shown up here. And so for the very last time, here is your pre-lecture example for this video, as well as a bonus follow-up. If you have any last questions on any of this material, be sure to bring them to class. Over and out.